Hello students, welcome back. Let's resume ourselves towards section 3. We had been discussing 0 over 0 type limits. First, we went through this example, which was pretty easy as a matter of fact. Plug in first, of course, and you get 0 over 0. So what's your strategy? Factor the numerator and denominator, and we ended up with monic trinomials for both. So the factorization computation was pretty easy. So we have x squared minus 4 factored like this, and x squared minus 3x plus 2 factored like that. Both are monic, so it's an easy factorization. So cancel those common factor x minus 2 out. What's left is a trivial limit. Plug in x equal to 2 and do your computation. Make sure you put the limit notations as they are. Now, what if you have something more complicated? Like this. In that case, you have to factor it using a little bit more advanced technique. So here, down here, let's increase the font. Factor 2 out. So 6, and then 13. And then 6, and then further factorization of denominator. Well, you can use tic-tac-toe method as I did, or some other method, whatever it is. If it works, it works. Go ahead and factor, and eliminate the common factor. What's left is a trivial limit, so plug in and do your computation. It may take a bit of an effort, factorization, but once the factorization is done, then just plugging in with the help of calculator. Okay, all right. Now, how about something like this? This one is fundamentally different. We cannot factor because we do not have polynomials there. How do we do that? If I plug it in, down here h is 0, here h is 0, so 1 minus 1. So it's a 0 over 0 type limit, all right? Then again, how do we handle this? Well, one way to handle the problem with square root is to consider the conjugate. Multiply the conjugate of this numerator to both numerator and denominator. So that's the conjugate. Change this negative to positive. That's the conjugate. And then multiply the same thing to both numerator and denominator so that I don't change anything. And then carefully FOIL out and do your computation. Denominator, h times square root, so h square root. And 1 times h, so we get that. Let's put some space in between. Now here, first, square root times square root. So square root of 1 plus h times square root of 1 plus h. So first, this square root times that square root is just 1 plus h. Make sense? Next, outside, this square root times 1. So 1 times anything is 1. So that's what you get from the outside. Inside, negative 1 times the square root, so minus of square root of 1 plus h. Finally, last, negative 1 times positive 1. And these two cancel out. They must cancel out. Otherwise, you wouldn't have multiplied the conjugate to begin with. Or you could use a minus b times a plus b, so that a squared minus b squared, so that you don't have to consider the middle part at all. I usually do it in the latter way. But most students I found like the previous method, FOIL out carefully. And if you do that, then that entire thing is gone. You end up with this limit computation. Can you simplify further? This 1 and the -1 will cancel each other out. And here, if I factor h out, I'll get 1. Oh, so this breaking off is counterproductive. I didn't have to do that. So let's not break off the denominator, just keep it, and then cross h out. So cross it out, so 1, and that's gone. And what do we have? Finally, we have a trivial limit. You can plug in h equal to 0. If you do that, we have 1 over square root of 1. Ooh, sorry about that. Square root of 1 plus 1, so this 1/2. So it was a bit tough to calculate this limit because it's not rational. It's not polynomial over polynomial. In that case, what do you do? There are 2 ways to handle it, and the other method will be discussed several weeks later, L'Hopital's rule. But right now, what you can do is to multiply by conjugate of both numerator and denominator here, change this minus to plus, and then FOIL out and do your computation. After some simplification, you end up with a trivial limit as before. What did I do here? Well, yeah, exactly the same computation. Same computation. Okay, that concludes 0 over 0 type limit. The simplest and the most important. Let's review again. Factor and make sure you put this limit notations. Again, factor and make sure you have all those limit notations. And here, multiply by conjugate and simplify. Again, we have to have all this limit notation until the very last moment when you're plugging in. Let's go to the next example. Infinity over infinity type limits. X is going to infinity, so if you plug in infinity, then infinity squared over infinity squared. Yes, it's infinity over infinity type limit. Same thing here, same thing there. Infinity over infinity type limit. Alright, how do we handle this problem here? And I have a limit solution here, limit rule solution here, excuse me. But I do not recommend it. Divide each by the leading term. X squared is highest degree term. Divide each by highest degree term and apply the limit rule. Let's see, can you follow that? Put limit there and limit and the denominator going to 0. Limit denominator is infinity, denominator is infinity, so something over infinity is going to 0. So they all go to 0 and then, yes, we have a limit computation. And this is our textbook's method. I don't like it very much, but here it is. Limit rule solution or the textbook solution is like this. Start with dividing by the highest degree term. But my preference is the practical solution here. The highest degree term dominates. That's much bigger than much smaller terms. 2x squared minus 8. 8 is very small compared with x is some gazillion squared. So just throw away 8. And 2 is negligible. 3x is of course much bigger, but compared with x squared, that's nothing. I mean, x squared, the highest degree term, is kind of like amount of water in the Atlantic Ocean or Pacific Ocean. And 3x, that's kind of like amount of water in Mississippi. That's a lot, yes, compared with finite terms, but compared with ocean water, pretty much nothing. So what we have, after crossing all those out, we get 2x squared over 2, so just 2. And this kind of expression is something we had been doing in college algebra class for horizontal asymptote computation. Remember that? We used to do something like this. Let's expand the font again. And asymptotically equivalent to this. And that's just 2. So this expression here, which I just highlighted in blue, and this expression here, which I highlighted in red, are not the same functions, but they're asymptotically equivalent. So as x gets really, really, really large, these two graphs get closer and closer and closer to each other. So this thing here and then this thing there, oh, I don't want color. Let's use this one. Well, equivalently, I could have just written 2, going from, say, okay, picture from -5 to +5. What do you see? They are very, very different. Now, from -15 to +15, oh, okay, all right. -50 to +50. Now, how do they behave? -100 to +100. You can clearly see the asymptotic behavior. So red and blue are not the same, two different curves, two different graphs, but asymptotically they behave the same. They share the same limit at infinity. So you cannot say these two are equal functions, but you can say their limits are equal. So this is actually wrong because this expression here, this equality is wrong, and this too is a bit problematic. This one is clearly wrong, but if you put limits, they're okay. And of course, if you want to get away from all those, then you can use this asymptotic equivalence notation, but that actually means the limit. I think that's what I wrote over here as a wrong solution. Yeah, this is wrong. This is not equality, especially this one. This is terribly wrong. And this one is also pretty problematic. But this one is clearly wrong. Now, if you put limits, then that's good. Well, that takes care of an easy problem. We have a couple of really important and hard problems left. We're going to do those in a separate video. See you soon.